Now we are going to observe some parameters. Now, but those parameters you can intuitively tell me. Right? 1. Can you fill in this inequality blank? What is it? So F is a flow. Let me write down, right? F is a flow. What is the value of the flow? It is the effective amount of current that is flowing out of S. That is V belonging to V, F of S comma V minus summation V belonging to V, F of V comma S. This is the net current or the net flow coming out of the vertex S. That is the definition of the value of the flow. Now, so this is S and this is a formula for the effective current. This fellow is the effective flow that is flowing from S to T. This is the effective flow that is going from S to T. What is the connection between the effective flow that is leaving S and the effective flow that is crossing over from S to T? Which direction is less than or equal to? This is less than or equal to, this is, it could be less than, is it? Where is the flow going then? You are pouring water into S, right? And you have conservation condition, it has to go out, right? At every vertex it has to cross, it has to leave, right? Whatever comes in should go out, right? So if you say it is strictly less than S, no, you said less than or equal to. So I am asking you, why did you say less than? So intuitively, because of the fact that conservation is respected at every node, we will boldly guess that it is actually equal to U, right? The picture is very clear. The right hand side is the effect of the net flow of current outside or leaving S. The left hand side is that you have taken the network and broken it into two parts, S and T. One side contains S, the other side contains T, right? And you are looking at the net flow that goes from S to T. Intuitively, both the values must be equal and we will formally prove it. We will write a sequence of equations which will essentially lead to this. Fine. So this is one more, this is the second thing that I should prove in the last 15 minutes. Next very interesting thing, right, is F of S comma T, and this is going to give us the upper bound, right? So I wish I could cut and paste. It is this formula, right? So let me write this formula again. It is summation V belonging to S, summation U belonging to T, F of V comma U minus summation V belonging to S, U belonging to T, F of U comma V. Fine. Because the flow is positive, this is lesser than or equal to negative term I will remove, the subtracted term I will remove. This is summation U belonging to S, whatever, okay. So this is U and V or V and U. V, U belonging to T, F of V comma U, right. Since F is non-negative. Actually, this is also lesser than or equal to, can you guess what would be the natural next step? Recall, we want to place an upper bound on this, and I have convinced you that I am going to prove you that these two are equal, and I am interested in an upper bound on this guy, because I do not know if the Ford Fulkerson algorithm will keep growing up to infinity. So I want to prove an upper bound. So I am coming towards an upper bound, starting from F, this is equal, this is lesser than or equal to this, right, for a particular flow. What is this lesser than or equal to? Capacity, right. So this is summation V belonging to S, summation U belonging to T, C of V comma U, because every flow respects the capacity of the edge. This is less than or equal to the capacity of S comma T. Right. what I did not emphasize, which I will emphasize now, is that consider any S and T cut. The value of the flow is less than or equal to the value of any ST cut. Right? If F is a flow and S union T is equal to V, S intersection T is equal to MT, S belongs to S, T belongs to T, then the value of this flow is going to be equal to f of s comma t. This is less than or equal to the capacity of this ST cut. In particular, the value of the flow is lesser than or equal to the value of the ST cut, the minimum ST cut. Fine. Actually, again, I like to present this in terms of electrical networks. Right? If you apply a 1 volt source across a point, across a pair of points in a resistive network, the amount of current that goes through it is exactly equal to the effective resistance of that network as seen from there. Right? So, V is equal to IR. Right? So, it is the amount of current will be equal to 1 divided by R, which would be the conductance of that particular network. Right? And therefore, the amount of current is that part which provides the maximum resistance or the minimum conductance. So, the min cut is same as the maximum resistance or the minimum conductance in a resistive network. I am assuming remember your electrical circuits, right. So, they are just the same, right. So, this is just a more generic framework in which this whole thing is presented. Right. So, therefore, the maximum flow is upper bounded by the minimum value of the ST cut. Now, I am going to complete the argument and show you that the maximum flow, this will be, so therefore, which are the things I should prove? This I have already proved, this I have to prove, this is the second term that I am supposed to prove, and the first one that the augmenting is a flow at its value, I have to prove that, which I will come to. Right. Now, I am ready to prove the max flow min cut theorem. Right. That deserves a new page. Right. It says the following are equivalent. The following three statements are equivalent. The first one, F is a max flow. 2, GF can somebody complete this for me? If F is a max flow in the given network G, no, residual network is GF, there is no ST path, super. Yeah, all of you are right. Right? Does not have an ST path, because if there is an ST path, you can increase the value of the flow. 3, there exists an S comma T such that f of st is equal to the capacity. What I showed you is that f of s comma t is less than or equal to the capacity. If you have a max flow, we will now, one direction you have already proved, 1 to 2 you have already proved. Now I am going to show you 2 to 3, right. So 1 to 2 is obvious, right, because if you find an ST path in GF, then you can increase the value of the flow, but F is a max flow, therefore there is no ST path. Now let us prove 2 to 3. The following are equivalent, which means we will prove 1 to 2, 2 to 3 and 3 to 4. It turns out that GF does not have an ST path. So what do? I have to now construct this ST partition. Right? Let us do this. So what do I do? S is equal to set of all S, can somebody guess what is S? The capital S. Remember what you should do, you have a max flow. You have a flow, somebody says it's a max flow. You constructed a residual network GF. There is no path from S to T. I want you to now give me a partition of the vertex set into S, capital S and capital T, such that capital S contains S and capital T contains T, the terminus T. So can you give me S? What is your idea? How do you, yeah, can you, that's correct, right? But what would be that cut? Because I want little bit more. I want to argue that the value of that flow is actually equal to the capacity of that cut. What would be that cut? So you simply take all the vertices which are reachable from S. So you take this residual network, take all the vertices which are reachable from S, right, in GF, fine, right, and T is equal to V minus S. Right, and T is equal to V minus S. Fine. Right. Now let's go to G. Right, consider G, consider S and consider T, right. In G, these were the edges which were present, right. Each one had a certain capacity. So maybe this is capacity U, V and so on and so forth, right. In GF, what has happened? All these edges have vanished. What does that mean if they have vanished? Which means their residual capacity is 0. Right? In GF, are you getting me? Can you see this? Right. So very interesting, tricky step, right? So GF does not have an augmenting path. So what do? You start at S and you you group all the vertices which are reachable from small s and you call that as capital S. That set you call it capital S. The complement is called T. Take this partition. You take this partition and go to G. In G it would have looked like this, right? Some edges are all there, right, and they all have some capacities. They might even be 0, right? Doesn't matter. Some capacities are there. In GF, all these edges have vanished. That's why there is no. Otherwise, you would have found one more vertex which is actually you put inside T, which should have been in S. All these edges are not there. Their residual capacity is 0. What is the formula for residual capacity for an edge which is present in the network? It is this formula, right? And that's equal to 0, which implies in your flow f of u comma v is equal to c of u comma v. Therefore, the capacity of the cut is equal to f of u comma v, right, which is greater than or equal to, right, sorry, right, no, this is greater than or equal to, well, I should not get lazy. Am I correct? Because I am subtracting a positive term. And what is the last term? What is this equal to? It's a value of f, which is f of s comma t. Right? I didn't say equal to yet. I only showed greater than or equal to. I proved the other direction. I'm sorry for jumping. I proved that for every cut, the value of f of s comma t is less than or equal to c of s comma t. That was easy, right? But now you see this. The trick here, if f is a max flow, gf does not have an augmenting path. If gf does not have an augmenting path, you start from s and you reach every vertex which is reachable from s, group it into s. Rest of them is called t, right? Now you do some logical analysis, right? You say, let me look at this partition s comma t in the graph G, right? Why is there no path from s to t in GF, right? Because all those edges have residual capacity 0. What is the definition of residual capacity? This is here, which means in the flow f of u comma v must be equal to c of u comma v. Now you write this chain of implications. C of s comma t is equal to this, by definition. This follows from this observation, right? And this is greater than or equal to the term where you subtract something more, and that is equal to f of s comma t. Therefore, when you have a max flow and you take the special partition, the capacity of the cut is at least as large as the flow. Therefore, the capacity of this cut is equal to f of s comma t. Fine. Yes, right. So the final claim, they can't be a smaller ST cut, no, because right. So if you have attained, right, so you know that a certain value is always lesser than or equal to the value of the minimum ST cut. Therefore, C of s comma t is the minimum ST cut, is the value of the minimum ST cut. The capacity of s comma t is the value of the minimum ST cut. So if you find the max flow, then look at all the vertices reachable from S, that is the minimum ST cut. Right. So this is the max flow min cut theorem. The other direction, 3 goes to 1, because I said Is there a question in this? Right. So this step is sequence of lot of small interesting observations. I've just proved that if you have a max flow, then there is a cut whose value is equal to the value of that max flow, and that cut is the minimum ST cut. Right. What is interesting, and I mean, I'm sure when you go back and read it, it will all become very clear. The cut is a graph theoretic parameter. A flow is something that I asked you to calculate, and it turns out that the maximum value for the flow is equal to this minimum graph theoretic parameter, the minimum value for this graph theoretic parameter. So that's the very interesting, I mean, third max-min relationship, right? So recall Menger's theorem, then we proved that maximum matching is equal to minimum vertex cover in bipartite graphs, and now we've shown that max flow is equal to the minimum cut in a flow network. I need to complete 3 goes to 1. What does 3 goes to 1 mean, right? If it's fairly easy from the definition of everything that we have discussed so far, right? So if you ever increase the value of the flow further, then the value of the flow will be more than the capacity of one particular cut, and that cannot happen, right? Therefore, F is a maximum flow. You cannot increase the value of this flow any further, because if one of you increases the value of the flow and claims that, I will ask you, how is it that you have increased the value beyond the value of a cut? We already proved that that cannot happen. Right? So this completes the proof of the max flow min cut theorem. Right? So I have about 6 minutes. So what I will do is, I will show you how to prove the 2 things that I have not yet proved. Right? So let me write them down, and okay, before that, are there questions? Okay. I need to prove 2 lemmas. Right? So for your interest, let me write this down. We need to argue that this is one thing to prove, and the second thing to prove is that so both of them are very similar, right? So to prove that, so what do you know? You know that F is a flow and F prime is a flow in GF. Right? So now let us prove that F augmented with F prime is a flow. So let us do this work of proving first thing. So let me erase this. I'll move this to a next slide. Right? These are the things that I should prove. Right? So what I will do is I'll just give you a flavor of what kind of algebra that you should do to complete these proofs. It's very easy, right? Just requires you to just play around with the equations a bit. So let us write down the definition of, right? You recall this is f of u comma v plus f prime of u comma v minus f prime of v comma u. Right? So let's tick off the positivity. Can somebody convince me that this is positive? Why is this greater than or equal to 0? There's a subtraction term. So you need to remember that F is a flow in G, F prime is a flow in GF, the residual network F. Why should this formula be positive, be non-negative? Right. Exactly, right. So now let us just look at this, right. So what she is basically pointing out is that this term is positive, right. This F prime of V comma U, right, for an edge which is present in the network, right, is actually the F of U comma V, right. So remember that you are looking at a particular edge, UV, right. Recall the definition, what you would have done, right. So you would have said F prime of V comma U by the definition of residual capacity would have been, sorry, I think that's not the way to say this, right. So if you look at F prime, then the value of this, right, is upper bounded by the residual capacity of Cf of V comma U. So let me write it that way. The first inequality is that this F prime of V comma U, right, is upper bounded by the residual capacity in F of V comma U, right, and the residual capacity, right, of Cf of U comma of V comma U, right. There are two possibilities here. Right. You might have written this as C of V comma U minus F of V comma U, right? No? Oh, the edge is UV only, right? Yeah, I'm sorry. Yeah. And yeah, I got it. Right. So let us just recall this, right? So I'm looking at this particular edge UV, right? And so therefore this would have actually been equal to F of U comma V, right? So let us just look at it. This is the definition of the residual network. You have UV. If you have a flow of F, then the capacity of this edge would have been F of, right, sorry, let me rename this correctly, F V comma U, right. The capacity of this edge would have been F of U comma V, right. These two would cancel, right. So therefore these two terms would cancel and this would be equal to, right, or rather this would be greater than or equal to F prime of U comma V, right, and this is greater than or equal to 0 because that was a positive value on the flow. Right. So by using the same inequality, let us just check. So therefore the positivity is taken care of. Let's check that you don't violate the capacity. Right. So what do you know? So you know that this term was not violating capacity, right. This is actually the residual capacity, right, F prime of U comma V. So this would have been, so therefore this term is lesser because of its positivity, right, because of the positivity of this, this is less than or equal to F of U comma V plus F prime of U comma V. But what is F prime of U comma V, right? So this is U comma V, this is U comma V. So this is equal to the capacity of U comma V in the network minus F of U comma V. That's the definition of the residual capacity, sorry. That's the definition of right. So F prime of U comma V is less than or equal to the residual capacity CF of U comma V, because f prime is a flow in the residual network, and Cf of u comma v is exactly equal to this value. Therefore, the augmented flow, that is f augmented with f prime, right, is this cancels and this cancels, right. So therefore, there are two things that we have taken care of, that this is greater than or equal to 0, the value, the augmented flow is greater than or equal to 0, and it does not violate capacity on any arc. Now we need to look at conservation. Okay. I think I'll just stop here, right, because most of this is just observations of, so when you look at conservation, you have to write down at any node, right, summation v any u other than s comma t, you have to write down that this is equal to f augmented with f prime, right, v comma u. Right. So what you do is you expand this formula out by using this definition at every place, and expand the right hand side also using this, and then you will see that things will neatly cancel. Right. So that's what I mean by saying, once you understand what this actually is, right, conservation and will be easy to verify. And similarly, to check that the value of this flow, right, is again combination of intuition and the algebra. Right. So I will just stop here and let me just summarize. Right. So we define network flows. We looked at the Ford-Fulkerson template. Right. We argued that it terminates integer capacities. Keep this in mind when you read a standard textbook Corman-Lyserson, you will see that the capacities can be real numbers for which Ford-Fulkerson algorithm will not terminate. Right. There are examples of flow networks. Actually, you can go and Google, right, just Google network flow instances for which Ford-Fulkerson does not terminate, and you will see a nice flow network where the Ford-Fulkerson algorithm will run forever. It will never reach the max flow. In the limit, it will reach the max flow, but it will never, in finite number of steps, achieve the maximum flow. Right. It's a very interesting thing. Because we put integer capacities, it will always terminate, right, and on termination, terminates with max flow, and we also proved that max flow is equal to the minimum SD cut. Okay. So what you will do next is try and look at interesting implementations of this.